Hello everybody, today we're going to be looking at algorithm analysis and in particular big O calculations. Big O notation provides a way to compare scalability of different algorithms, and then we can decide to make trade-offs about which algorithm we use. For the purposes of today, we'll look at these three different n values, n squared, and the logarithm of n. There are many more that we could use, but these three will give us a nice little trade-off where we can see how different algorithms scale at different size n. Now, when we discuss n, this is the size of your input into your particular data structure. So often this will be the size of your array or how many items are in your stack. You can think of it as general data points. We'll go ahead and input n with this numpad over here. We'll start out with something relatively low, like 3 that we can see across n squared, and log n. For the sake of n, we can consider this a loop that loops through an array of size 3. As you can see, to do that, it would take 3 operations, as represented by the balls here. For n squared, think of this as a loop embedded inside of another loop. So for this, for every item n, we have to go through that loop n times. So 3 times 3, you'll see that we have 9 balls here represented in green. For logarithm of n, you'll see that it only takes 1 operation to go through it. Now, for representation purposes, this doesn't matter if it's log base 2 or log base 10. It'll scale the same way in a logarithmic form. Now, big O calculation is a worst case scenario of a particular algorithm or data structure's performance. So 3 does not give us a great representation of how something may scale. So we're going to go ahead and bump this up to 10. Now, the worst case scenario for big O of n would be that we have to run all 10 operations. So this is a linear scale. Now, n squared becomes a little more interesting here, with 10 squared being 100. While 10 is not an amazingly large n, you can at least hear that it is dramatically different between n squared and n. Since this one's going to take a while to run, we went ahead and ran log n while that was running, and you can see log n of 10 is only 3 operations. These balls represent the worst case scenario for each one of these types of algorithms. So this would be one pass through that algorithm, but you could foreseeably see that you might run these algorithms more than once depending on what type of system you're in. So I think quite clearly from this, you can see that we could run log n algorithms many more times than we can run n or n squared doing this. We'll go ahead and finish this segment by running n squared another time, just so you can see the worst case scenario of running this multiple times. Let's go ahead and repeat this exercise one more time, but with a much larger n. So we'll use n equals 100 here, and look at n squared, and log n one more time. So at higher n's, the difference in these type of algorithms really become noticeable. I'll try to hit these in quick fashion so we can see them run together. You'll see log of n has already finished with 6 operations. N is still going, and n squared is still going here. So while there may be a limited amount of algorithms that can be solved in log n time, clearly when presented with the opportunity, you want to follow along with these. So here we go, n has finally finished here. Quite a bit more than log n, but you can see still much better than n squared that's still running. Now, n squared will take quite a bit of time to finish here, more than we can show in this little segment. So we'll go ahead and give these another run here so you can see how quickly these other ones can finish in the same amount of time that the first run of n squared is still going. Go ahead and click log n a few more times so we can see just how many times this one runs. It's really good. Now, while this is finishing up, we can say there are situations where you just can't get away from an n squared algorithm, or something even worse like n factorial. So depending on the problem you're trying to solve, this may be the reality that you're in. Now, I want us to take a look at a particular big O value. So in this case, we'll look at O of n, and I want us to look across different values of n. So we'll start out with 10 here and take a look at what it looks like. We saw this in the previous one. Let's go ahead and double n here. So we'll go ahead and make it 20 where we can, and we'll look at n once again. And what we want to see with n is that this scales in a linear fashion, right? So this is called a linear scaling algorithm. So what we should see here is more or less a double in the amount of balls that we're seeing from red to green. Let's go ahead and double this one more time. So we'll go ahead and make it 40 here, and we'll run in the third block here, big O of n yet again. So as this comes down, if this is our worst case scenario for an algorithm, notice here that it kind of goes up like a y equals x line, right? So this kind of linear scaling, very predictable, and overall a really good type of algorithm that the more data that we get, it's predictable in its linear scale. Now let's go ahead and repeat this exercise, but let's do it for n squared. So I'm going to use smaller numbers here. Let's start with 2 maybe, and we can look at n squared and how it scales with different values across these 3 blocks. So 2 squared is 4. We get 4 blocks on this low one. We can go ahead and double that. Let's look at 4 and 4 squared, and we'll see how that scales. You should start to see as these come down that it starts to form something that looks like a graph of y equals x squared. We saw with big O of n that it looked like y equals x, kind of a straight line. This one should start to look like a curving line upwards. We'll go ahead and double it again for n equals 8, and you can start to see 8 squared. We get 64 blocks on this. So you can start to see as n increases, this really scales poorly. While O of n was a linear scaling algorithm, O of n squared is considered a quadratic scaling algorithm. So we're going to repeat the scaling exercise one more time, but we're going to look at our best algorithm, logarithmic scaling here. So we'll look at log of n. In previous examples, this was able to compute with very few executions. So in this example, we'll be able to use some larger numbers. So we'll go ahead and start with n equals 100 here. We can see with n equals 100, this only takes 6 operations to compute. That's really good. Let's go ahead and add a 0 to this. So let's look at n equals 1000. So much larger than anything we've looked at up to this point. So when we hit log of n here, we'll see how many come down in the green balls section. And we get approximately 9 operations. So to go from 100 data points to 1000, it only took an additional 3 operations. That's pretty good. You'll see this kind of efficiency on binary search trees and some of our tree algorithms later on. So for this last one, we're going to go ahead and add another 0 and go up to n equals 10,000. This should give us way more examples. And as we run this, you see, it finishes pretty quickly. For going to 10,000 data points, we actually only have about 13 operations or executions needed here. All right, so we were able to execute way more pieces of data for only a handful of more operations. For anyone who's had to search through an array or linear time operation, hopefully you can appreciate how efficient that is. Let's go ahead and raise it up even more, and let's do 1,000,000 operations. I'll go ahead and add it to the red balls here since that only had a few operations for it. You can see, while certainly more, it's not dramatically more. If you go back to some of our n squared operations, we can still calculate this much faster than we were doing n squared for relatively low n.